MA161, Chapter 4.3, Logarithmic Functions and Their Applications. Okay, logarithm, we will learn logarithm. So as you see here, let's say log, okay, y equals log base b of x, if and only if b to the yth power is equal to x. Okay, log, how do you read this one? Log bx. This means the logarithm of logarithm base b of x. Okay, base b. The little letter b is written just below this log, on the right side of log, with a lower, small number, small case. So we call this logarithm base x of x. And this logarithm, okay, let me rewrite this. Y equals, okay, logarithm base b of x. Let's say this is equal to y. Then you can convert this into an exponential form. So the base for the exponential form, this base of this logarithm will be the base. And the exponent of this base will be this y. So y will be the exponent of the base b, and the result will be this x. So this is how we convert from logarithm to exponential form. Okay, let's try again. Little bit confused. So let's say we have logarithm base 10 of x. Let's say this is equal to y. Then once you convert this to an exponential form, use the same base 10, and the exponent of this 10 will be y. The other, go to the other side of the equation. So y will be the exponent. Then the result will be the logarithm inside the logarithm. So x. Okay, let's try another one. Just an example. The logarithm base b base 10 of x is equal to, let's say this is equal to 2. And then how do you find x? Okay, just rewrite the logarithm into the exponential form. So base 10 raised to the second power, so that should be equal to x. So once you simplify this, the left side of the equation is 100, so that x will be 100. This is how we convert logarithm into an exponential form. How about exponential form? So let's say here is the base b, and raised to the x power is equal to y. Then you can do the same thing. This base will be the base of the logarithm, so log base b of, so this y will goes inside the logarithm, so the result will be x, like this. Okay, let's try again. B to the let's say okay, let's use base 10 to the x, exponent is x. Then let's say this is equal to 100. Then we want to find the x, so you can try this. Logarithm base 10, so this base will be the logarithm, the base of the logarithm, and then this 100 goes inside the logarithm, so the result will be x. Okay, so just rewriting exponential form into logarithm or vice versa. So based on this, let's try another example. Okay, there are four very important properties. So here it is property 1, 2, 3, and 4. Okay, the first one is this. The logarithm base, let's say base, base can be any number that is not equal to 0. It should be positive but not equal to 1. The base has to be positive but not equal to 1. So let's say the logarithm base 10 of 10. So inside the logarithm and the base are same. If they are both same, then this is equal to 1. Always is equal to 1. So if you have logarithm base b of b, then this is equal to 1. Okay, there's another one. Okay, the second one is this, logarithm base b. Logarithm base b of 1. If 1 is inside the logarithm, then this is equal to always 0. So when the log of x, if x is equal to 1, if logarithm log of 1, if this is log of 1, then the result is 0. So if x equals 1, then the logarithm will become 0. Okay, number 3. Number 3 is also really simple. Here's the log base b. And inside the logarithm is an exponential form whose base is b and the exponent is x. And then you can take this exponent to the front. That exponent moves to the front, so x times logarithm base b of b. So from the property number 1, logarithm base b of b is equal to 1. This is equal to 1. So x times 1, so this is equal to x. This is so fun, huh? Because the base is b, and inside the logarithm is b to the x power exponential form, whose base is b. Then you can just take this x out. Take the x out. Okay, how about the fourth property? Okay, the fourth property is an exponential form. Base is b, and the exponent is logarithm. Exponent is logarithm. The base of the logarithm is b of x. Then you can get rid of this exponent, the base b and the logarithm b. So this will be simply an x. So there are 4 properties that we use a lot. So please remember this. You can memorize these properties. Base b of b is equal to 1. Logarithm of 1 is always 0. And logarithm base b of b to the x power. If this is an exponential form, then you can take this x out. And the fourth property is base b. Okay, exponential form has base b, but the exponent is logarithm base b. Same base, then you can take this x out. Okay, let's try some example. Example 1. Okay, let's rewrite this equation in the exponential form. Okay, exponential form using our methods earlier. The base is 2, so you can write it as base 2 as an exponential form, and the exponent will be the other one, will be the other side, 3. So 3 will be the exponent, then the result will be inside the logarithm 8. So this is an exponential form. Or you can do this way, using our property. Okay, let's use our property. Okay, the property number b. Let's try number 4, the fourth one. Okay, let's take a base 2. Since this is 2, let's make an exponential form on each side. Take an exponential form on each side. So make a base 2. Then the left hand side is 2 cubed. The left hand side is 2 cubed. The right side, this thing can cancel out, and only this 8 can get out. Because the exponential form, the base is 2 and the logarithm base is 2, this whole thing cancel out, we get 8. Now this is the property number 4. So we have the same exponential equation. Okay, let's try letter B. Okay, letter B is 2 is equal to logarithm base 10 of x plus 5. So we can let's use both methods. since the base is 10, write an exponential form with the base 10. Then the exponent will be the other side, which is 2. Then the result will be inside the logarithm, x plus 5. Okay, and let's try another method. Let's take the base 10 on each side. So we'll take base, the base is 10, so let's take base 10 on each side. Then left side is 10 squared. The right side is, you can remove all these things out, so we have x plus 5 left. Okay, let's try another one. Let us see. Logarithm base e x is equal to 4. Alright, do the same thing. The base is e, so take the base e, then the power is the other side, 4, and then the result is inside the logarithm. Okay, let's make an exponential form. Exponential form. Since the base of the logarithm is e, take e as base of the exponential form in each side. Then the left side is only x. Left side, this whole thing cancel out, so we have x is equal to e to the 4th power. Okay, another one, letter D. Logarithm base b of b cubed is equal to 3. Alright, the base is b, so the exponential form is b to the, okay, b is the base and 3 is the exponent of the exponential form. The result is inside the logarithm. Inside the logarithm is this guy, b cubed. Okay. Alright, and then using the property, okay, the logarithm, inside the logarithm is an exponential form. Then you can take this exponent out. So this will be 3 times logarithm base b of b is equal to 3. Okay, this means we are just, and then the base of the logarithm and inside are the same, so this will be 1. So 3 times 1 is equal to 3. So the answer will be 3 times 3. Okay, actually we want to write an exponential form, right? Exponential form. So, okay, let me rewrite the question so that we can make an exponential form, which is same as the left hand side. Okay, here's the logarithm base b of b cubed is equal to 3. We don't need this parenthesis. Okay, so from here, let's take base b on each side. Base b, base b. Then this will be removed. So we have only b cubed left. B cubed, and the right side is b cubed. So this is the exponential form, which is same as the result using the first method. Example 2. Okay, for this example, we will write this equation in its logarithmic form. Okay, logarithmic form. Okay, the base is 3. This exponential form has the base 3. So for the logarithm, we will use the same base. So logarithm base 3. And the inside, the logarithm will be 9 in the other side. The result will be the exponent 2. Okay, let's try another one. Okay, 5 cubed is equal to x. Do the same thing. The left side is an exponential form, and the base is 5. The base is 5. So write the logarithm with the same base 5, and then the other side x goes inside the logarithm, and the result is the exponent 3. Okay, let's keep trying. A to the bth power is equal to c. The base of this exponential form is a, so make sure the base of the logarithm is same as a, and then the other side c will be the inside the logarithm, and the result is the exponent b. Okay, letter D. B to the exponent is logarithm base b of 5 is equal to 5. Still same thing. The left side of the equation is an exponential form, and the base is b, so make sure to have the same base b of the logarithm. So logarithm base b of the outside 5 is equal to the exponent. Logarithm base b of 5. Okay, exercise 3. We will evaluate the logarithm. So let's simplify this. If the logarithm of 1, if this is 1, then it's always equal to what? If this value is 1, then the result is always 0. It's a property. The logarithm base b of x. And if x equals 1, if x is equal to 1, okay, base b is okay. You can, if x equals 1, then the result is equal to 0. Okay, letter B. Logarithm base 5 of 5. The base 5 and the inside is same, then this is equal to always 1. Okay, why? Well, let's use a property. Okay, let me just write it as equal to y. Let's say this logarithm is equal to y. Then using the exponential form, 5 to the y is equal to 5 to the y is equal to, the result is 5. Then the exponent of this 5 is equal to 1. From these equations, bases are the same, 5 and 5. So the exponents must be equal to the same. So y should be equal to 1. So y is the logarithm. So y is this logarithm. So the result is 1. So this is equal to 1. That means logarithm base 5 of 5 is equal to 1. Okay, let's try letter C. Logarithm base 2 of 2 to the 4th power. Using the definition, you can take this exponent to the front. So this is 4 times. Okay, 4 times logarithm base 2 of 2. Then logarithm base 2 of 2 is equal to 1. So 4 times 1 is equal to 4. Okay, letter D. 3 log, exponent is log base 3 of 7. Since the base and the logarithm base are the same, you can get rid of this, so the result is 7. Okay, let's try a little bit more examples. Okay, when we evaluate this logarithm base 10 of 100, then we can write this logarithm base 10, and this 100 is 10 squared. So using the property, this exponent moves to the front, and the logarithm base 10 of base 10, logarithm base 10 of 10 is equal to 1, so this is equal to 2. Okay, the next one, 64 is 4 cubed. So if we rewrite it, logarithm base 4 of 4 cubed. And this cube moves to the front, and the rest is same. The rest is 1. So logarithm base 4 of 4 is equal to 1. So 3 times 1 equals 3. Okay, the last one is logarithm base 7. Okay, 1 over 40, 1 over 49 is 7 squared. Then you can rewrite it. so that we will have the same base. So this fraction is 7 to the negative second power, because 7 squared moved to the numerator, then change the exponent sign. Then finally this negative 2 exponent moves to the front, then that is logarithm 7 base 7 of 7. So negative 2 times 1 is equal to negative 2. Okay, let's find out the graph of logarithm functions. Okay, first of all, let's go the graph of exponential form e to the x. The graph of g of x is equal to the x, then okay, if x equals 0, then y equals 1. If x equals 1, then y is 2 to the 1, so it will be 2. Let's say this is 2, or something like this. And the graph of g of x is something like this. Okay, this is the graph of g of x. And when we flip this, okay, reflect across this equation, y equals x. Then the graph is the logarithm base 2 of x. So actually f prime of this f of x is the inverse function of g of x. So if it's an inverse function, then what we do is switch x and y. So okay, this point is x equals 0, y equals 1, and this point is x equals 1 and y equals 2. So what we do is flip this x and y. So this point will be 1, 0. So this point moves to this, and this point moves to over here. This is 2. So the graph looks like this. So this is the graph of logarithm. So for the logarithm, if x equals 1, then y is always 0. X equals 1, y equals 0. So if x for the logarithm function, if x is less than 1 and greater than 0, then the logarithm value is negative. As you see this, negative value. So if x is greater than 1, then the logarithm is positive. Okay, positive value. Okay, how about what if we have another function? Let's say k of x is equal to 3 to the x power. 3 to the x power. Okay, let me use the green card. 3 to the x power. Okay, erase it. 3 to the x power. Then the graph will be this. X equals 0, then y equals 0. X equals 1, then y will be 3. So the graph is more skinny like this. So this one is close to the y-axis. Then L of x, let's say L of x is equal to, use a different color, okay, this one. L of x is equal to logarithm base 3 of x. 3 of x, so L of x is the inverse function of function k, inverse of function k. And the graph is, as you can see, this 3 to the x power, the graph is close to the y-axis. So this time, same thing. This value will be when x equals 1, y equals 3. So this point will be when x equals 3, y is equal to 1. So maybe over here. Oh, not this one, sorry. Undo. Here. 1, x equals 3, y equals 1. Because interchange is 1 and 3. So this will be 3 and 1. So this is also close to the x-axis. The graph is close to the x-axis, like this. Like this. So whenever the base is larger, then the graph is close to the y-axis or close to the x-axis. Exercise 5. In this exercise, we will find the domain of the logarithm. Okay, actually, the domain, let's say y is equal to logarithm of x. Then the graph is always, looks like this, and the x-intercept is always 1. So when x equals 1, then the logarithm is 0. And in this case, the domain x value is always greater than 0. Always greater than 0. And this y-axis is the vertical asymptote. So the x should be always greater than 0, not equal to 0. Must be just greater than 0. So this x, inside the logarithm, must be greater than 0. So for the domain of this one is this x plus x minus 3 must be equal to 0. So the domain comes from x minus 3, which is greater than 0. And then solve for x. So plus 3 each side, so that x is greater than 3. So this is the domain. Okay, how about b? F of x is equal to logarithm to absolute value of x plus 2. Okay, absolute value of x, this one. The logarithm, inside the logarithm is absolute value. This one is already greater than, is equal to 0. This one is greater than, okay, we want this to be greater than 0, not equal to 0. So absolute value is always greater than or equal to 0. We want this to be 0. So, okay, let me write this. Absolute value of x plus 2 is equal to 0. Then when we solve this, okay, how do you make this one 0? You know, x plus 2, absolute value x plus equal to 0, that means this will be 0 when x equals 2 and negative 2. X is 2 and negative 2, this will be equal to 0. So from this condition, we want the absolute value is greater than or equal to 0, so this will be outside these numbers. As long as x is not equal to 2 and negative 2, so they all satisfies. So x should be less than negative 2, or x is between negative 2 and 2, or x has to be greater than 2. So x can be all real number except 2 and negative 2, because this absolute value should be greater than 0, cannot be equal to 0. Oops, I'm sorry, actually, okay, absolute value is equal to 0, so when x equals negative 2, this absolute value is equal to 0. So 2 is not included. I'm sorry, 2 is not included. Never mind this one. Not included. So x is all real number. X is all real number except negative 2. So that x is less than negative 2, or x should be greater than negative 2. So x is all real number. So the domain is all real number x, except x is negative 2. This means all real number. Okay, the domain comes from inside the logarithm. So this parenthesis must be greater than 0. So x over 8 minus x has to be greater than 0. So let's find the interval so that this rational expression is positive. So let's find the critical numbers. Okay, the critical numbers come from the numerator by setting the numerator equal to 0, and by setting the denominator is equal to 0. So set the numerator is equal to 0, and set the denominator equal to 0. Then x equals 0, and from here x is equal to 8. So based on these critical numbers, here is 0 and here is 8. And 0, so we cannot include these numbers, because if we include these numbers, if we include 0, then the numerator is 0, so this rational expression is 0. And if x equals 8, then the denominator is 0, so it's undefined. So we will not include 0 and 8. And there are three intervals. So let's check sign of each interval. So if x is less than 0, let's try -1. Then -1 over x is -1, so this is positive. 8 minus -1 is positive. So negative or positive is, this is negative. So this part is negative. Between, if x is between 0 and 8, let's try 1. X equals 1. Numerator is 1. Denominator is 1. Then plug in 1. Then 8 minus 1 is negative. So positive over, the denominator is positive. So positive over positive is the positive. Okay, if x is greater than 8, let's use 9. The 9, then the numerator is positive. The denominator is 8 minus 9 is negative. So positive over negative means negative. So from these three intervals, the only the positive part is between 0 and 8. So that's the domain. So the domain is x is between 0 and 8. Or you can write it as starting from 0 all the way up to 8. But 0 and 8 is not included, so use parentheses. So this is interval notation, this is inequality notation. Okay, exercise 6, graph the logarithm. Okay, when we graph the logarithm, okay, the parent function, the graph of the parent function, let's say y equals log of x. Then the graph of logarithm x is always something like this. And the base is 4. 4 means this one, if the base gets larger, then the graph gets close to the x-axis. Okay, now this is translation. X is increased by 3. That means shift the graph of logarithm x. This is logarithm base 4 of x. So shift this graph 3 units to the left. So 1, 2, 3. -1, -2. This is -3. And -3 is the vertical asymptote, because we are shifting 3 units to the left. So everything moves 3 units to the left. So the graph will be something like this. And the y-intercept is when x equals 0, we get the y-intercept. So x equals 0, then this is the logarithm base 4 over of 3, this part. Okay, next graph is logarithm base 4 of x. Okay, this is the logarithm. Okay, when x equals 1, always y equals 0. So this is logarithm base 4 of x, the parent function. And then plus 3 means y. This y value is increased by 3. So we will shift this one 3 units up. 1, 2, 3. Shift this 3 units up. So that looks like this. So shift this point 3 units up. 1, 2, 3 up. Okay, here is two types of logarithm. One is called common logarithmic function. The other one is natural logarithmic function. Okay, common logarithmic function is the logarithm base 10. If the base is 10, then we usually do not write this base 10. Okay, we usually do not write this base 10. So it will be log of x. So if you have a log of x like this, that means the base is always 10. We call this common logarithm. Common logarithm. So this means base is always 10. Okay, how about if the base is e? If the base is e, then we use ln. Ln is natural log. Instead of logarithm, we use ln, natural log of x. So we call this natural logarithm. So whenever you have ln x, then the base of the logarithm is always e. Okay, e. The value of e is 2.71. This is irrational number. 2.71. 2.71. Something like this. 71, 81, 82, and so on. Okay, so natural logarithm, common logarithm. The base of the natural logarithm is e, and it can be written in ln, not log, not log. Use ln, natural log. And if the base is 10, then we usually do not write the base, and then write it as logarithm of x, log of x. Okay, let's compare the graph of this too. Okay, for the graph of natural logarithm x, then what is the base? Okay, the base is equal to e. The base is equal to e, which is 2.71. And the common logarithm, the base is equal to 10. So 10 is greater than e, 2.71. So the graph of logarithm, common logarithm looks like this. So the graph will be close to the x-axis. So logarithm log of x will be close to the x-axis, and the natural logarithm is a little bit further from the x-axis. Let's say this is y-axis. So this will be the natural log, graph of the natural logarithm, and this will be the graph of the natural logarithm. Okay. Again, this red graph is the graph of the common logarithm, and this green graph, this graph in green is the graph of the natural logarithm.